So in today's lecture, we're going to derive the Schrödinger equation. However, before we do that, let's remind ourselves of the challenge that Schrödinger had to solve. So according to the old quantum mechanics, which is what we've been discussing so far, so let's call that old. It wasn't really a theory of mechanics, so let's just call it old quantum theory. According to the old quantum theory, we had a collection of rules of thumb to dealing with various situations. So for example, we knew that light was a particle, and that was supported by the explanation of the photoelectric effect, the Frank-Hertz experiment, the Bohr atom, Compton experiment, and such experiments. However, we also knew from even before quantum mechanics that light was a wave. So in interference experiment, light manifested its wave behavior. And then there were other things such as, atoms and molecules had quantized energy states. That was another thing. And we saw the case of the hydrogen atom, or any atom that was whose orbits were roughly circular. And then there was the case of matter waves. So de Broglie proposed that there were these things called matter waves, which described certain quantum properties of small particles. And after de Broglie proposed his de Broglie relationships, there were experiments done by Davison and Germer, where they diffracted some electron beams from an atom, with an element which had a lattice structure, and they found that the pattern of the electron beam after the diffraction, showed the interference pattern that one expects from waves being diffracted from a diffraction grating. So there were all these ad hoc rules, but what was really missing was an underlying principle. So there were all these ad hoc rules, but what was missing was an underlying principle. So after de Broglie discovered that one can associate waves to small particles, it was a challenge to find an equation for a wave, that is a wave equation from which the de Broglie relationships, in which the de Broglie relationships fit in naturally. So what do I mean by that? So remember the de Broglie relationships. The energy is given by h bar omega, and the momentum is given by h bar k. So now suppose that we are dealing with a non-relativistic particle. So an electron at low velocity is a non-relativistic particle. So it has some energy. So it has some kinetic energy, which is p squared by 2m, and it's in some potential. So we have some v of x. Then if I use the de Broglie relationship in this equation, then I get a constraint on the relationship between omega and k. So what is that constraint? We get the constraint, which is h bar omega has to be equal to h bar squared k squared divided by 2m plus the potential energy. So the challenge was to come up with a wave equation from which this will follow naturally. So this is going to be our challenge for today.